transformer, when fans are operational, can deliver approximately 1600 amps at full load, corresponding to its 1333 kVA rating. However, without the fans operational, the transformer's capacity is derated due to reduced cooling efficiency. This could limit it to the 1000 kVA nameplate rating, resulting in a possible ampacity of 1200 amps. It's crucial to consult the transformer's nameplate and manufacturer's specifications for exact derating factors when operating without fans. A power factor of 90% does not derate the transformer's KVA rating. The KVA rating is based on apparent power, which includes both real power and reactive power. Power factor only affects the relationship between real and reactive power, but not the apparent power. In summary, if the fans are not operational, the transformer's capacity may be limited to 1000 kVA, yielding approximately 1200 amps. The transformer's KVA rating remains unaffected by the power factor. To elaborate on transformer operation with and without cooling fans, it's important to understand the fundamental principles of heat dissipation in transformers. Transformers generate heat due to losses within the core and windings. These losses, often referred to as iron losses, core losses, and copper losses, winding losses, are a byproduct of the electromagnetic processes occurring within the transformer. The heat generated must be effectively removed to prevent the transformer from overheating, which can lead to insulation degradation and ultimately transformer failure. Cooling fans significantly enhance the rate at which heat is dissipated from the transformer. They achieve this by increasing the airflow over the cooling surfaces, such as the radiators or cooling fins that are typically attached to the transformer's tank. This increased airflow promotes convective heat transfer, which is the process of heat removal through the movement of a fluid, in this case air. When the cooling fans are not operational, the rate of heat dissipation is reduced, and the transformer's temperature rises more quickly under load. To prevent overheating, the transformer's load must be reduced or derated. The amount of derating required depends on several factors, including the transformer's design, the ambient temperature, and the specific cooling system employed. Transformer manufacturers typically provide derating curves or tables that specify the allowable load as a function of ambient temperature and cooling system status. These curves are essential for ensuring that the transformer operates within its safe temperature limits. The derating process involves reducing the amount of current that the transformer is allowed to supply. This is because the heat generated within the transformer is directly proportional to the square of the current flowing through the windings. By reducing the current, the heat generation is reduced, and the transformer's temperature is kept within acceptable limits. The 1000 kVA rating you mentioned likely represents the transformer's self-cooled capacity, meaning the capacity it can handle without the assistance of cooling fans. The 1333 kVA rating represents the forced air-cooled capacity, meaning the capacity it can handle when the cooling fans are operational. The difference between these two ratings highlights the significant impact that cooling fans have on the transformer's overall capacity. Now, let's delve into the concept of power factor and its relationship to transformer operation. Power factor is a measure of how effectively electrical power is being used. It is defined as the ratio of real power, measured in kilowatts, to apparent power, measured in kVA. Real power represents the power that is actually used to perform work, while apparent power represents the total power that is being supplied to the circuit. The difference between real power and apparent power is due to reactive power, which is the power that is stored and released by reactive components such as inductors and capacitors. A power factor of 1.0 or 100% indicates that all of the power being supplied to the circuit is being used to perform work. A power factor of less than 1.0 indicates that some of the power is being used to support reactive loads. While a low power factor does not directly derate the transformer's KVA rating, it can have several negative consequences. Firstly, a low power factor increases the current flowing through the transformer windings. This is because the apparent power is higher than the real power, and the current is proportional to the apparent power. The increased current can lead to increased copper losses and higher operating temperatures. Secondly, a low power factor can reduce the voltage regulation of the transformer. Voltage regulation is a measure of how well the transformer maintains a constant output voltage under varying load conditions. A low power factor can cause the output voltage to drop more significantly as the load increases. Thirdly, a low power factor can increase the overall cost of electricity. Utility companies often charge customers a penalty for operating with a low power factor, as it increases the burden on the electrical grid. To improve power factor correction equipment such as capacitors can be installed. These capacitors provide reactive power to offset the reactive power drawn by inductive loads, such as motors and transformers. By improving the power factor, the current flowing through the transformer windings is reduced, the voltage regulation is improved, and the overall cost of electricity is lowered. It is important to note that while a low power factor does not directly direct the transformer's KVA rating, it can indirectly affect the transformer's performance and lifespan. Therefore, it is important to maintain a high power factor to ensure efficient and reliable transformer operation. In summary, the transformer's KVA rating is determined by its design and cooling system, not by the power factor. However, the power factor can affect the transformer's operating temperature, voltage regulation, and overall efficiency. Therefore, it is important to consider both the KVA rating and the power factor when selecting and operating a transformer. Moreover, regular maintenance is crucial for ensuring the longevity and efficient operation of transformers, including the cooling system. Firstly, inspect cooling fans for proper operation. Verify that all fans are running smoothly and that there are no obstructions preventing airflow. Replace any damaged or malfunctioning fans promptly. Secondly, clean cooling fins and radiators. Dust and debris can accumulate on cooling surfaces, reducing their ability to dissipate heat effectively. Regularly clean these surfaces using a brush or vacuum cleaner. Thirdly, monitor transformer temperature. Use temperature sensors or infrared cameras to monitor the transformer's temperature under various load conditions. Compare these readings to the manufacturer's specifications to ensure that the transformer is operating within its safe temperature limits. Fourthly, check oil levels and condition. For oil-filled transformers, regularly check the oil level and condition. Low oil levels can reduce cooling efficiency, and contaminated oil can degrade insulation. Sample the oil periodically and test it for dielectric strength, acidity, and other contaminants. Fifthly, inspect bushings and connections. Check the transformer's bushings and connections for signs of damage or corrosion. Clean and tighten any loose connections and replace any damaged components. Sixthly, perform insulation resistance testing. Regularly perform insulation resistance testing to assess the condition of the transformer's insulation. Low insulation resistance can indicate insulation degradation and the need for repair or replacement. Seventhly, check for leaks. Inspect the transformer for oil leaks or other signs of fluid leakage. Address any leaks promptly to prevent environmental contamination and potential equipment damage. Eighthly, review load profiles. Analyze the transformer's load profile to identify any patterns or trends that may indicate potential problems. Overloading or frequent cycling can accelerate insulation degradation and reduce the transformer's lifespan. Ninthly, verify proper grounding. Ensure that the transformer is properly grounded to protect against electrical faults and prevent damage to equipment and personnel. Tenthly, keep records. Maintain detailed records of all inspections, maintenance activities, and test results. This information can be used to track the transformer's performance over time and identify potential problems early on. By following these maintenance practices, you can extend the lifespan of your transformer, improve its efficiency, and reduce the risk of costly failures. Furthermore, understanding the specific directing factors provided by the transformer manufacturer is essential for safe and efficient operation when cooling fans are not functioning. These factors take into account the transformer's design and the specific cooling system in place. Directing curves or tables will typically specify the allowable load as a percentage of the nameplate rating for different ambient temperatures and cooling conditions. It is important to adhere to these directing factors to prevent overheating and potential damage to the transformer. Also, consider installing temperature monitoring devices on the transformer to provide real-time data on its operating temperature. These devices can be configured to trigger alarms if the temperature exceeds safe limits, allowing for timely intervention to prevent overheating. Remember that operating a transformer without adequate cooling can significantly reduce its lifespan and increase the risk of failure. Therefore, it is crucial to ensure that the cooling system is functioning properly at all times. If the cooling fans are not operational, the transformer's load must be reduced accordingly, following the manufacturer's rating guidelines. By understanding the principles of heat dissipation, power factor, and proper maintenance practices, you can ensure the safe, efficient, and reliable operation of your transformer.